So today we're going to take a look at solving some exponential equations, and in particular we're going to be taking a look at that third log law, which you can see that looks like our power rule that we were using. And we're going to see how that applies to solving some different equations. So we have to solve number one. It says we have 4 to the x equals 8, and we're going to solve it in 2 different methods, either using common bases or the log law. So common bases we have done before, where we would take a look and say we need to take each of these sides, get a common base, make smaller. So I'm thinking with 4, if I make this smaller, I could express 4 as 2 squared. We still have raised to the x. Whereas 8, I could express that as 2 cubed. So now they have the common base of 2. And in order to solve, I want to set my exponents equal. Here I want to think power raised to a power we multiply. So by setting them equal, I can solve and find x is 3/2 or 1.5. A different approach is to use the log approach. So the same equation that we're going to start off with here, but what we're going to do is introduce a log on each side. Remember, if you do one to one side, you got to do one to the other. Okay, so we introduce a log, and now I see this exponent. Well, from that power rule, our exponent can come down in front. So now I have x times log of 4 equals log of 8. And I can solve for x by dividing through with log of 4. Now, the nice thing with this is you can just type this into your calculator to solve. And if we were to type that in, I would say let's get a fraction template. We're going to use our log button, so control the log button. Now it's a common log. I don't have to put a base 10 in if I don't want to. I can just arrow over and do log of 8 and then divided by, and again we're going to have here log of 4. And I press enter, and notice that's going to get us that same answer of 1.5, or again we could express it as 3/2. Okay, so those are 2 different options that we can use to solve these exponential equations. So this will always work. This will work with any function, whether I can get common bases or not. The nice thing with this is if I can't get common bases, because not all problems will give you common bases, such as these next ones, then using that log law would be a great way to solve these equations. So for this first one, I cannot find a base 5 that when I raise it to any exponent would give me 18. So here's where we'd want to introduce a log. And I want to introduce a log again to each side. Okay. Keeping in mind that when I have that exponent can come down in front. So now I'm getting something like x times the log of 5 equals the log of 18. And so to divide through by log of 5 is going to give me my final answer. So again, if we did this in our calculator, I would do my fraction template. We would have log of, and again, it's a common log base 10, so I don't have to type that in. Log of 18 divided by our log of 5, and we get our answer. It's about 1.795, and if we rounded it to the nearest hundredth, that would get us about 1.80. So I can say here, x is equal to 1.80. Okay, we'll try one more. Same idea. I'm going to introduce a log to each side. So if I were to introduce a log here and introduce a log here, that exponent comes down in front. So I get x times log of 4 equals log of 100. And if we divide through by log of 4, so again, grab our calculator, and get a fraction template. We're going to do log of 100, and then we're going to divide that by log of 4, round to the nearest hundredth. So our nearest hundredth here is about 3.32. Okay. I'll leave letter C for you to try if you'd like to try. It's going to get you an answer of about 10.61. Okay, next one's very similar. It's just now we have variables. Okay, so we're going to use that log law again, same idea. It's just now we have to actually solve for x. So we have to do a little bit more work. Step number one, again, we're going to introduce a log. I can't get common bases, so since I can't, that would be my clue to saying let's introduce a log on each side. Now we have that exponent, so that exponent can come down in front using that power rule. Notice I put that in parentheses because it's that whole quantity x plus 3 that is coming down. And so trying to solve for x, keep in mind this is all being multiplied. I'd want to divide through by log of 6 first. And so on this side I get x plus 3 is equal to, and I could keep this all as, let's say, log of 50 divided by log of 6, or I could get it as a number. Okay, I'm doing that because then at the end, I could subtract over 3, and now I could enter this whole thing into my calculator all at once. So I could do, again, we'll get our fraction template. We're going to do log of 50, and arrow down, and do log of 6. And then I'm just going to arrow over to the side and make sure I get right next to that fraction. And I'm going to subtract out the 3, and we're going to get our final answer. Now, if we round to the nearest hundredth, we're going to get negative 0.82 for our final answer. So I can say x is negative 0.82. Okay. Same idea with this. It's just we have a fraction. So again, if we introduce a log to each side, this whole exponent comes down in front. So now I get x over 2 minus 5 times the log of 1.03. And then on the right-hand side, we have the log of 2. Okay, we're trying to solve for x. And since these things are being multiplied, the very first thing I can do is divide through by log of 1.03. Okay, so we reduce those out here. So we have x over 2 minus 5. And now we can plug all of that into the calculator. Log of 2 divided by log of 1.03. And we get about 23.4498. Okay, so from here I'm solving for x. Next step I would think is let's add over that 5. So I have x over 2 is equal to about 28. And now to get x by itself, I want to think multiply each side by 2. So if I multiply this by 2, the 2's cancel out and I'm left with x. And if we multiply that by 2, our final answer, round to the nearest hundredth, we get about 56.90. Okay, so we have a formula that we're going to take a look at. And this kind of looks familiar to a formula that we have used in the past. And we use this with our exponential modeling. So it says a quantity Q is known to increase by a fixed percentage in decimal form, then Q can be modeled by. And it says Q sub 0 represents the amount of Q present at time 0, and T represents time. We've seen something very similar. We have that A, similar formula was our A equals P times 1 plus R to the T. Extremely similar formula. We got some different numbers here. So, biologist is modeling the population of bats on a tropical island. When he first starts observing them, there are 104 bats. So that's our initial population is what like we would say, or principal. The biologist believes that the bat population is growing at a rate of 3% per year. So now again, 3%, we want to think to ourselves when we're using this in the formula, turn it into a decimal. Move that decimal point over 2 places to the left. So we're going to write an equation for the number of bats as a function of the number of years. Okay, so number of bats according to time, function of time. So we start off with that P value, or that Q sub 0 value, that's your initial amount that we have, times 1 plus P, P being the rate, and our rate we said was 0.03. And then we have our exponent. So very similar to what we had before. All right, we could simplify this. This is going to be 104 times 1.03 to the T. So now it says we're going to use that equation from part A to algebraically determine the number of years it will take for the population to reach 200. So before, when we did this, we would just graph out 200, and then we would graph out this other equation. We would see where they would intersect. Well, now using our log properties, we're able to solve this algebraically. And what we want to do is we want to get everything away from the thing with the exponents. So like I want to get everything away from this number 1.03. So I'm going to first start by dividing through by 104. Okay, and that's going to leave me with around 1.9 and change. And on this side, I still have 1.03t. Okay, what I'm trying to do is solve for t. T is an exponent. So with our log properties, I could introduce a log to each side, and that allows me to bring that exponent down in front. So now everything's on one line. Okay, so now t is down in front. It's being multiplied by log of 1.03. And now, like we did in our other problems, I can divide each side through by the log of 1.03. And now we get t. So this reduces out. And t, when we plug that in, turns out to be, with our rounding, you get like 22.123. So with our rounding, that's going to round to around 22 for the nearest year. Okay, so now we have a method to solve these algebraically. Okay, we'll try another one. So we have a stock has been declining at a price, in price at steady pace of about 5% per week. It says if the stock started at a price of $22.50 per share, determine algebraically the number of weeks it will take for the price to reach $10. Okay, so again, I want to think my initial starting amount that I have is $22.50. We're going to multiply that by 1, and then our rate. And since we're declining, I need to think subtracting out our rate expressed as a decimal. And then I know it needs to equal $10. That's my final amount. I want to know how much time it's going to take. Okay, so there's our equation. Step number 1, again, I want to get everything away from this parentheses that's attached to the exponent. So I can move this 2250 over. And I'm going to divide each side by that 2250. That's how we're going to move it. Okay, so now here, and again, I simplify that. That's going to give me 0.95t. And on this side, if I divide this out, we get about 0.44. So I need the exponent. I need the exponent to come down. So we have to introduce our logs to bring that exponent down. Okay. So now we have the equation log of 0.44 is equal to t log of 0.95. And again, solving for t, if I divide through each side by log of 0.95, we're going to find t. We divide that all in our calculator. T is going to be about 16.0056. But if we want to the nearest week, we're going to say it's going to be about 16 weeks. Okay. And so one last thing we're going to take a look at. So using your calculator, we can see we've always taken a look. It says the common log or common log base 10. We can always express our answers in terms of logs. And it says we're going to find the solution to each of the following exponential equations in terms of a log with the same base as the exponential equation. Okay, lots of words, but let's see what that means. All that means is let's again try and solve for x. So my goal is to get everything away from the number that's attached to the exponent. So everything's got to move away from this 2. So step 1, we're going to add the 3 over. Okay. Step 2, like we would have done up above, looks very similar. Divide through by 4. So now I have 2 to the x is equal to 5. Okay, so our log laws, I could introduce a log, and that x comes down in front. Okay, so now we have something that looks like x log of 2 is equal to log of 5, and I could divide through by log of 2. And so now we get something that looks like x equals log of 5 over log of 2, and we could put that in your calculator and we could get an answer. Okay, but now the question, what the question wanted us to do is it says we want to try and put this in terms of a log with the same base as the exponential equation. So that means let's go back to this line right here. I want to write that as a log with the same base as this exponential equation. The base here is a base 2. So go back to our whole change of base where we would always say base to the answer equals the number. Okay, so base raised to the answer equals the number. So if we want to turn this back into a log equation, we kind of have to undo that property. So this is the log. Here's our base. So our base 2 is our log base 2. The number 5, equals the answer. Our answer is x. So all we're doing is we're kind of taking that problem and like undoing our problem, going backwards. Okay, we'll try one more of these. So without solving it all the way through, we're just going to write it as that exponential equation. Okay, step number 1, divide through by 17. So now I have 5 to the x over 3 is equal to 4 over 17. Okay, so we have our exponential equation. I need a log base with this exponential base. So we're going to think to ourselves, this is the base raised to the answer, and this guy's the number. Okay, so we have log base 5 of our number equals our answer. And so we have solved by writing it as a log function. Okay. And I have a mistake here because I forgot a 3. I forgot we have a variable that's a 3. Okay, so we're not done yet. We're going to do one more thing here. So how else could I do this? Well, this would have an exponent attached to it. So I could, if I wanted to solve for x, right? Try to get x by itself, I got to cross multiply one more time. So I got to bring this 3 over here, multiply each side through by 3, multiply this through by 3. And so now really our final answer. Let's try this. Sorry, that was my bad. I forgot our exponent had a 3 on the side. So this here is our final answer. Okay, we'll do more of this in class. I hope this helped, and I hope you guys have a great day.